Question 2. Block 1 of mass 1 kilogram is M1 equals 1 kilogram. Connected over an ideal massless and frictionless pulley. I love those pulleys. Very expensive though. To block 2, mass of M2 equals 0.25 kilograms as shown. Assume that the blocks accelerate as shown, so there's the acceleration with acceleration magnitude A, and that the coefficient of kinetic friction, so I'll put a little k there, between block 2 and the plane is mu equals 0.2. Okay, let's go back to the pen here. So it's saying the velocity of each block at this moment is in the same direction as its acceleration. Okay, so it's going up this way, which means that the force of kinetic friction is down and to the right for M2. The angle of the incline is 30 degrees. Good. What is the magnitude of the acceleration A? Okay, so I'm going to start by drawing a free body diagrams. So let's draw a free body diagram for M1. So M1 is just hanging there, so it's got a tension pulling it upwards, and it's got gravity pulling it downwards, M1 times G. So we can do Newton's second law. We will say that we'll just define down to be positive y. We'll say F net in the y direction is equal to m times a. This is m1 times a is equal to downward is m1g minus the upward is t. So we'll solve for t because that's going to be our unknown. You'll say that t from mass 1 is equal to m1g minus m1 times a. I'm going to call this equation 1 because I'm going to end up using that later. And that same tension is carried across the pulley to M2. So now let's do a free body diagram for M2. Label it free body diagram for M2. So there's the M2. It's got now its tension is acting up and towards the left. It's got its kinetic friction acting down and towards the right because the velocity is up and towards the left. We've got the normal force acting out of off the plane, and there's gravity, which is going to be acting straight down, and that's m2 times g. It's the force of gravity. So 3 of these forces are either parallel or perpendicular to the plane, and only gravity is the odd one out. So what I'm going to do is set my y-axis to be away from the plane and the x-axis to be along it. And in fact, actually, I want to change that. I want the acceleration in the x direction to be the same as the downward acceleration for m1. So I'm going to choose x to actually be up the plane, so that A is acceleration in the plus x direction from the way I've set this up. Direction. Okay, so good. So now we can do our little table that I like to do, where we have x components and y components and the forces. So the forces here, let's list them. There's the normal force, there's the tension force, there's the kinetic friction, which we know is going to be equal to mu kinetic times normal. It has a nice equation for it. And there's mg, m2g. So we can figure out x and y components for all of these and then add them up to get our net forces. So the x component, or the normal force, with our axes drawn like this, is 0. Its y component is an unknown. I'm going to call it n. For tension, we know that it actually is in the positive x direction. I actually probably know it from equation 1, but I'm just going to write it as t for now. And it has 0 y component. The kinetic friction I'm going to write as negative x direction, and I might as well write in the mu sub k times normal. So normal is the unknown, and it has no y component. Now m2g, that's the one that's at an angle. So I'm going to just refer to a little diagram over here. Here's m2g, is the hypotenuse, and I need to figure out the components of this in the x and y direction. So actually, let's draw that on the other side. It's going to have a component in the negative x direction, negative m2g in the x direction, and then it's going to have a perpendicular component in the negative y direction, so negative m2g in the y direction, and the theta of the slope, the 30 degrees, is right there, and there's the right angle triangle, and this is m2g. So it takes a little practice to draw these triangles properly, but I can see from this diagram that the sine is going to be opposite over adjacent, so I always have to write this out. Sine theta is opposite, so m2g in the x direction, negative, divided by m2g, the hypotenuse. So the x component of this is going to be negative m2 times g times sine of theta. And similarly, I'm going to have the y component to be negative m2g times cosine of theta. And I'm going to sum these up to get f net. Okay. And I know that f net in the x direction is going to be equal to m2, this is object 2, times its acceleration. And f net in the y direction is, do you know it? 0, right? It's not accelerating in or out of the plane. So that's the nice easy one. So let's start with the y component. F net y equals 0 is, let's sum these up, normal force plus 0 plus 0, let's write it down, plus 0, minus m2g cos theta. And this allows us to solve for the normal force.